NASA just found a monster black hole in the center of a quasar. Pwehi. The phrase, embellished dark wellspring of everlasting creation, is used in the Kumalipo, a Hawaiian word that describes the origin of the universe. Simply put, it signifies horror in Maori. Supergiant galaxy Messier 87 in the constellation of Virgo is home to the monstrous, scary behemoth known as Pwehi. It was first seen to those of us on Earth in April 2019. Hi guys, welcome back to Beyond Unknown. Today we'll be taking a look at what NASA just found in the center of a quasar. Make sure to stick till the end of this video as we have a lot to cover. Also, don't forget to subscribe to our channel and like today's video. It helps us a long way. And let's get started. The awe-inspiring image of Pwehi was captured by the Event Horizon Telescope, a network of 8 ground-based radio observatories strategically placed around the world. Given the size and distance to the source, it was a remarkable achievement. Consider yourself sitting in a Parisian cafe, peering through your telescope at a New York newspaper. That is what it took to capture this incredible image in such exquisite detail. But what is this abomination, this mysterious source? Pwehi is a gigantic black hole that is billions of times as large as the Sun. Gravity is being pushed to its terrible extreme. The effect of gravity on light has already been demonstrated. What happens as the gravitational field is increased and space-time is curved more and more? You build a prison. When light is bent to such a degree that it becomes caught and unable to escape, nothing else can either. Pwehi is a prison for the forgotten, a cosmic oubliette, and an intolerant inferno. Such atrocities were first imagined by an English preacher. Reverend John Mitchell hypothesized the existence of dark stars in November 1783. Dark stars are enormous astronomical phenomena that are 500 times bigger than the Sun and have gravitational pulls that are so powerful that light itself cannot escape. Though it would soon be forgotten, the concept of invisible giants hiding in plain sight was thrilling at the time. This was due to the fact that it was founded on the corpuscular hypothesis, which held that light is composed of particles. Following Thomas Young's investigations at the turn of the 19th century, this theory was eventually replaced by a wave-like model. Despite the fact that Mitchell's research on black holes would be disregarded for nearly 2 centuries, he would go down in science history as the founder of seismology. He proposed that the disastrous earthquake and tsunami that rocked Lisbon in 1755 were caused by faults in the Earth's crust, rather than by atmospheric disturbances in his research on the event. The majority of scientists nowadays are certain that black holes do in fact exist. They typically develop when a star that is sufficiently massive, at least 20 times heavier than the Sun, runs out of fuel. Nuclear fusion is how stars generate their own energy. In their cores, atomic nuclei are compressed and squeezed together to form a furnace of constantly bursting thermonuclear bombs. By exerting outward thermal pressure to oppose the effects of gravity, this force keeps the star from collapsing under the weight of itself. But it's not permanent. The star can no longer support its own weight once it has produced too much iron in its core, rendering the fusion processes ineffective. Death Star. The star is swiftly overcome by gravity, which forces it inward like a garrote that gets tighter and tighter. Then, bang! In a stunning response to gravity's unrelenting assault, the star fights back. The neutrons, subatomic particles in the star core, are the ones carrying the battle. Whenever they are forced too closely together, they aggressively oppose one another through a powerful nuclear force. Material from the outer layers falls inward, smacks into the stationary neutron core, and bounces back. The star bursts in an instant as a pressure wave travels to its surface. A galaxy briefly being eclipsed by a supernova, a catastrophic occurrence. What remains? Undoubtedly a neutron star, an object with such high density that a teaspoonful of its material would weigh as much as a mountain on Earth. The neutron star has a chance of surviving if its overall mass can remain under that of 3 suns. Any more weight will cause the gravitational garrote to once again start to tighten. Neutrons won't be able to do anything. The situation will be hopeless. There is no stopping the collapse now, At some point, the star's density prevents light from escaping. The event horizon, the entrance to the cosmic oubliette, is a spheroidal surface past which there is no way back. It is where everything that once was the star is hidden. A star that is hefty enough to have its life eaten by gravity occurs about once in 1,000 stars. These dark remains of the biggest and most potent stars that have ever lived are known as stellar mass black holes, and they may be found all around the galaxy. But Pwehi is so much more than that. Pwehi has a mass of 6.5 billion suns, although black holes created by star death normally weigh between 5 and 10 suns. A leviathan, a supermassive black hole, is the focal point of a large galaxy located more than 50 million light-years away. Sagittarius A, the 4 million solar mass black hole at the core of the Milky Way, is smaller than our own leviathan, Pwehi. The event horizon distinguishes a black hole from other objects. On its surface, you would need to move at the speed of light just to remain motionless. It would be deadly to approach the horizon for a black hole of stellar mass. This is strange in a way since, as we've already established, gravity is fictitious and can be disproved at any time by stepping inside a darkened phone booth and plummeting, whether it's from the Burj Khalifa or in the direction of a black hole's event horizon. The issue is that as the gravitational field gets stronger, and as space-time gets more tightly curved, the area over which we can eliminate it, the size of the telephone box, gets less and smaller. Gravitational stress gradients that are too large to ignore exist outside of the box and are in danger of becoming much larger. A stellar mass black hole's horizon lies too near the well's bottom, and if you were to approach it too closely, the tides of gravity would rip you apart. However, because the bottom of the well is farther away from a supergiant black hole like Pwehi, it is unremarkable to pass past the horizon. Your days are numbered once you've passed this point, though. Literally. There will be an end to time. In the center of a black hole is a singularity, a location where space-time meets infinity, and the gravitational field expands without limit. It is the end of time, not space, that the singularity represents. Your journey through space-time will take you there once you have crossed the event horizon, while there is no such thing as tomorrow, and where there is no such thing as the future, not even in theory. The atoms in your body are ripped apart, the nuclei split into protons and neutrons, and the protons and neutrons are split into their constituent quarks and gluons as you draw closer to this Armageddon. These tremendous tidal and gravitational strains stretch you out like a string of spaghetti. The finality will arrive at the singularity, a merciful inevitability, and whatever consciousness is left will seek it out. Time will not halt for objects far from the horizon, but if they approach too closely, it will slow down significantly. In theory, you could visit these for a while, slow down time, and then return to Earth hurled years into the future if the black hole had enough spin to support stable planetary orbits that veer very close to the horizon. In the movie Interstellar, the crew of the Endurance visits Miller's planet, which revolves around the enormous black hole known as Gargantua, and experiences the full power of gravitational time dilation. Miller's planet can orbit Gargantua within a few thousandths of a percent of the horizon radius, since it is thought to be spinning so quickly, within a trillionth of a percent of the theoretical maximum. And that ends our episode. We hope you enjoyed our video. Please subscribe and leave a comment down below your own thoughts, and don't forget to like our video. And we'll see you in the next one. Thanks for watching.